This is the last video lecture of week 1. We're going to define and study the basic properties of measures. We start from the abstract definition of measure and main properties. Then we describe the Lebesgue measure and talk about probability measures. So definition and the main properties of measures. So here the definition of a measure. First, we need to start with a measurable space. Measurable space is a definition that we saw at the very beginning of the video lecture Sigma Algebras and Algebras. So that's a sample space and a class of subsets of the sample space which forms a sigma algebra. Then a function mu that assigns to each element of this family, and elements of this family, they are subsets of omega, a non-negative number which is allowed to be 0. It's allowed to take any positive number as its value, and it's also allowed to take plus infinity as a value. So this is a subset of the extended real line. So such a function, in order for it to be called measure, it has to satisfy two properties. The first one, the measure of the empty set is 0. And the second one is the measure of a countable union of disjoint sets, all of which are members of the sigma algebra, is given by the countable sum of the measure of each of these sets alone. So this is true for every sequence. This must be true for every sequence of sets in this family, countable sequence of disjoint sets. Because to have this equality here, we need them to be disjoint. Once we have a measurable space and a function mu that satisfy these two properties, we can call mu a measure on this measurable space. And now the triple omega, f, and mu is called a measure space. Now some convenient terminology. If we say that mu is sigma finite, f we can write omega as a countable union of sets, all of which have finite measure. Okay, so it's a countable union. All these sets in this sequence, they must be elements of the sigma algebra F. They must have finite measure, and the union of those has to be the entire set omega. Here is a very simple example of a measure. It's called Dirac mass measure, so it's named after Dirac, and it's the following. For a given sample space, we can take the family, the sigma algebra is the family of all subsets of the sample space omega, it does not matter, and let's fix a point in the sample space. Then we define a measure that is denoted by this letter delta, sub-index x, to indicate that x is a parameter in this definition, and it's defined as follows. The measure of a set A will be 1 if x belongs to A and 0 if x does not belong to A, which can be described here as the indicator function of the set A at the point x. So this is the indicator that x belongs to A. This is a finite measure. Yes, of course it is a finite measure, because then the measure delta x of the entire sample space omega, it is 1, so it is finite. And it is also a probability measure. We have not yet defined probability measures, but this is also a probability measure. Now from this small measure, the Dirac mass measure, we can build a huge measure called the counting measure. It is the following. We start with a non-empty set, so omega is a sample space. Then we consider again the sigma algebra of all subsets of omega, and we're going to define a measure mu to be summing this previous measure that puts mass 1 at the point x, we're going to sum this over all possible elements x in omega. And what does this mean? It means the measure of any set A will be just summing over all x delta x of A, which is the same as the number of elements in A. So this function here, it just counts how many elements are in A. If it is 0 if A is empty, it will be 7 if A has 7 elements, and it will be infinite if A has infinitely many elements. It does not matter countable or uncountable. The case where the sample space omega is finite gives a finite measure. And the case when omega is infinite but countable, then this is a sigma finite measure, and I let you figure out why. Let's see some examples of measures. Let's take omega as the set of natural numbers, excluding 0. F to be again the sigma algebra of all subsets of the natural numbers. And we define the measure of a set A. We define this function mu that assigns to a set A and this sigma algebra, which means any subset A of the set of natural numbers. It will assign to that set A the sum of 1 over k. This is 1 over k, where k should range over all elements of the set A. Then we can show, and I'll let you figure out the proof, we can show that mu is a measure, first of all, and not only it is a measure, it is a sigma finite measure. Now the other example is the restriction of the function mu to a smaller class of set, which we call coarsening. Why coarsening? Because if a sigma algebra is contained in another sigma algebra, we say that this one, the second one, is finer and the first one is coarser. So if we have a measure space and now we consider a smaller sigma algebra, which is called a sub-sigma algebra, G is a sub-sigma algebra of F, then this triple here is also a measure space. Of course, here the function mu here is the restriction of this function mu to a smaller set of its domain. Namely, we only allow this function mu here to be evaluated at elements of G. This is a measure space, and I let you figure out why. Each time we see y, question mark inside parentheses in the slides or in the lecture notes, it means it is an exercise for you to complete by yourselves. Now here is another example of how to build a new measure from an old one. So we start again from a measure space, which has a sample space, a sigma algebra, and a measure. And suppose we have some measurable set, which means a set, a member of this, an element of this sigma algebra. Then we can define the restriction of the measure mu to the set A. We denote this by mu restricted A, like this, and this is given as follows. The measure of any set B, the restricted measure of any set B, will be just the measure of the parts of B that overlap with A. Okay? And this is also a measure, and I let you figure out why this is a measure, prove this, and write down a complete proof that this verify the 3 properties that we ask for, 2, in fact, properties of a measure.